Welcome. In this lecture video, we're going to take a look at the requirements for drawing accurate and correct free body diagrams in physics. A lot of times the key to solving problems using Newton's second law is to draw an accurate diagram of all of the forces acting on an object, and that's all we do with a free body diagram. Draw an accurate diagram of all the forces acting on an object. So here we have a block sitting on Earth, and for the time being we're going to say in the absence of friction between the block and the floor, this block is at rest. So it's on Earth. We know that there is going to be a force of gravity acting on the object. And so I have drawn this gravitational force acting on the center of mass of the block, going straight down, and I have labeled it. And in general, in my class, I would like you to draw your free body diagrams like this, with the forces acting on the object's center of mass. We will get into cases where we will draw forces acting on the object at the point of action, but for right now, let's just draw our free body diagrams with all forces originating at the center. There is also a force from the ground pushing up. This would be a normal force, so I could label it N. And notice the object is at rest, so I have drawn my normal force and my gravitational force with the same magnitude, the same length, equal and opposite. All right? Well, let's say that someone comes along and starts to push this block to the right, still in the absence of friction. Then I can add on another force here, F sub P, maybe for push force. Notice I'm not labeling any of my forces with the same label. You cannot do that unless the forces are the same. And so now, let's say we are not ignoring friction, and let's say in this case the block is accelerating to the right. So my push force then must be larger than the force of friction. So if the block is accelerating, we know we have unbalanced forces, and if we have unbalanced forces, we get an acceleration. So notice how I have drawn my push force larger than my frictional force. All right? If the object is accelerating, you better have more force acting in the direction of the acceleration. All right, per Newton's second law. And that will be nitpicked on if you didn't draw the lengths of the vectors relatively appropriate. You don't have to get out a ruler or anything on this, but if it's accelerating to the right, your force going to the right better be longer than your force going to the left. Okay? So here let's take a look at a system of two masses connected by strings to a ceiling. The system is at rest, so the acceleration is equal to 0. So I better have equal and opposite forces acting on all of these objects, balanced forces. So it's usually easiest when you deal with systems of masses to draw the free body diagram for the object that has the least amount of forces acting on it. And in this case, that's going to be M2. So I'm going to draw my free body diagram for M2 on a little dot. And a lot of times on exams, that's what you're asked to do. On the dot that represents M2, draw all of the forces acting. So in this case, we have gravity going down, which I'll say is M2 times G, because that's how you would calculate the force of gravity on M2. And then I have a tension force in the string going up, which I'm going to call T1. T1 to differentiate it from the tension force in the upper string. So M2 is not accelerating, balanced forces, the downward force is equal in length to the upward force. So now on this dot over here, representing M1, let's label these guys M2 and M1. Let's draw all of the forces acting on M1. It's easiest to start with gravity. So we have M1G going down. Now, here's where Newton's third law comes into play, because if M2 is being pulled up by the tension force in the string, then M1 has to be pulled down by that exact same tension force. So this is a Newton's third law pair. In essence, through the string, M1 pulls up on M2. That means M2 pulls down on M1. So I'm going to be very careful with this tension force that I draw in here, and make sure that it is about equal in length to the T1 that I drew up here. And I can label these the same because they are equal in magnitude. So we have T1 pulling up on M2, and we have T1 pulling down on M1. So now the tension force in the upper string, well, I know that M1 is not accelerating. So I better draw that about so that it about balances with the two downward forces. Again, I'm not going to break out a ruler, but T2 better be larger than T1, and T2 better be approximately equal to whatever T1 plus M1G is. And that would be the correct free body diagram for that situation. All right? Be careful with your T1 and M1G. All of the forces acting have to originate on the dot or touch the dot. All right? So be careful that your arrows are somehow touching the dot. Again, in general, in my class, I want the arrows originating from the dot, which represents the center of the object. Here we have another famous case of a system of masses where we have to apply Newton's third law. M1 and M2 are in contact with each other. And always, 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 when two objects are in contact with each other, there is a contact force. And that contact force needs to be equal in magnitude and opposite in direction, acting on the two objects. Always. There are no exceptions to this rule. Your contact forces will always be equal in magnitude and acting opposite in direction on the different objects. And that's true of tensional forces in ropes as well, as long as the ropes don't have mass. So going back to the previous problem here, that tensional force T1 that's pulling up on M2 is always going to be equal and opposite to the T1 pulling down, as long as the rope doesn't have mass. And in general, we're not dealing with massive ropes. We can ignore it. So let's draw some free body diagrams here. We will do M2 first, because that has the least amount of forces acting on it. So M2, we've got gravity going down at M2G, and then we have this contact force going up, and that is M1 pushing up on M2. All right, so going over here to the free body diagram for M1, I'm going to immediately draw in that contact force going straight down and about equal in length to that contact force going up. Always Newton's third law. M1 pushes up on M2, M2 pushes down on M1 with an equal and opposite force. Always, always, always. All right? So we also have a gravitational force going down, and I'm going to draw that right here, M1G. And then now we have the floor pushing up on M1. The floor only pushes on M1 because the floor is not touching M2. The floor can't apply a force to M2 without touching it. So again, I'm going to draw this quite large, showing that it's counteracting both the contact force and M1G. And my forces are balanced here because M1 is not accelerating. So when we draw a free body diagram, especially for these systems, you need to be very careful. You only include the forces that are acting on that object. Okay, so I was very careful and said, oh, the floor is only pushing up on M1. The floor is not touching M2. All right, M1 is touching M2. It is M1's contact force that pushes up on M2. And those contact forces are Newton's third law pairs. Okay, one pushes up on M2, and an equal and opposite force pushes down on M1. And again, always, 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 when you have objects in contact with one another, you have to have those forces be equal in magnitude and opposite in direction. And also notice that these contact forces act on different objects. All right, the contact force here acts on M2. The contact force here acts on M1. Okay, it's not the interaction there that means this system is at rest. It's the interaction between those other forces in the system as a whole, which means they're at rest. It's the interaction between FC and M2G, which means M2 is at rest. And it's the interaction between all three forces over here, which means M1 is at rest. But why is the system at rest? Well, you can ignore that contact force because it's an internal force and it goes away. So it's the interaction between M2G, the normal force, and M1G, which causes that system to be at rest. So in review, make sure that you draw your forces acting on the center of the object. Make sure that all of your forces are labeled appropriately, and make sure that the lengths of your vectors are in the correct direction and are showing the correct length in terms of balanced versus unbalanced. All right, you always have to look at the acceleration. That's it for now.